Now the fourth one is the intermediate code generation. So somehow we have to, compiler tries to convert your source code into some intermediate presentation. The parse tree we just saw is also one of the intermediate presentations. But now we want something more like a machine language, okay? So that kind of intermediate code presentation. Now we need to keep two things in mind. One is that it should be easy to produce and easy to convert into the target machine language. Okay, so we saw the previous phases. We have the presentation as well. Similarly, in this intermediate core generation, we have also our our presentation. And this is one of the presentations. This is not basically one. Okay, this is not pertinent to particular machine. Okay, we're not writing to the specific machine, rather it is some abstract machine, writing to some abstract machine. Okay. Important thing in this is that it is something low level, and it's like machine-like intermediate representation, and where every operand is like a register. Okay. One of the such representations is this representation, which is like an assembly code, and it is actually called the three address intermediate code presentation. So, or three address code basically. In this three address representation, the important thing to note down is that we have at most one operator on the right, not two operators, something like that. As you can see here, it's one operator. So this also gives us the precedence because multiplication has to be done first, then the plus, and so on. Okay, so this presentation actually solves the precedence rules as well, and actually we take up this later on as a chapter where we see the complete details of how to do intermediate code presentation for we may have loops, we may have functions, we may have a lot of constructs. Okay, so we have to study all those things. So now the next step will be the code optimization. So until now we have a situation like this. For example, we got a equals b plus c into 60, for example. Firstly, the lexical analyzer do what? It generates the tokens, identifies the lexemes, and uses the symbol table to locate these ABC, and uses the 1, 2, and 3 to actually the symbol table entries. And then the syntax analyzer actually or a parser actually creates a parse tree. We discussed that. And the semantic analyzer actually tries to see the sense out of the syntax, and we did one change, a little change here into float, and then because we construct them to be as a floating point numbers, these guys, and 60 is an integer constant. Then intermediate code generator tries to generate some machine-like code, assembly-like code. Okay, not machine-like, because we have to convert this into the machine language. That is kind of easy. Then now this code is gonna be fed to the code optimizer. Okay, so now we'll talk about the code optimizer a little bit here because it's an introductory lecture. Now in this stage, the code optimization stage, after the intermediate code generation, if we go for a code optimization, this will lead to a much better target code generation. Okay, so code optimization is done for a lot of things. I may write those things a little bit. Important thing to note in this code optimization is this is machine independent code optimization. So this is machine independent code optimization. That's important, right? And this is done so that our code will run faster. It will use less resources like memory, registers. It will have fewer fetches. There are a lot of things we can do so that our later on when we convert this to target code, it's much better and much faster code. Maybe it will consume less power as well. Okay. So there could be a lot of things. We will try to see them later on in detail as well. If you look at our on top here, this this guy. We said we have a t1 equals into float 60, and then this t1 is multiplied to the id3, and that is put into t2. We can combine these two guys, right? So that this into float, we know that 60 is gonna be converted to the float. Why not to write it something like 60.0, isn't it? So when you are converting, when you have converted this intermediate code, when you have created an intermediate code, why not to optimize it, and instead of converting this 60 to into float, that means we are telling to convert it to a floating point, make it a floating point. It's much better. So we can combine them. So there's no need of this T1 statement at all. So we could combine these two, and there's no need of this T2 actually. So we can say only T1 equals to ID3 into T1 into 60.0. So we can replace it easily as T1 equals to ID3, okay, into, that is our in fact C, into 60.0, isn't it? Okay, and then we can combine these two guys as well, because here we have a 3 errors machine, so here we are only assigning things. Why not to write like this, ID1, which I want to, that is A equals to, because our question was A equals to B into C times 60. Now C times 60 is done here, ID3 into 60. Okay, this is the one statement. Okay, the next we want to do is to assign A, that is ID1, the B will be in the ID2, and whatever is this thing, this has happened into the T1, so multiplies T1. This is 3 errors, not a problem, we can do that if it's a plus. And now we have only 2 statements left. So previously we had 4 statements, now we have 2 statements. So this is the kind of optimization we are talking about. Okay, but it's not the only thing we will be doing. We will be doing a lot of things. We'll take them as a chapter later on, and we'll see what kind of optimization we can do. Say for example, also we have somewhere like this. Say for example, where's my pen? Oh, it's gone. Here. Say for example, I have like this. Let us put A equals to B plus C. So I have calculated B plus C and put that in the A somewhere. And then later on, I am saying D equals to say Z plus B plus C. Say for example like this. Okay. Now since we have a calculate B plus C, we can replace this here in the code optimization as this statement as D is equal to Z plus A. So this will actually we don't have to calculate B plus C again, because we have done it already. So we can do it. Okay, so this sub expression is eliminated, so we can say we can eliminate sub expression. We can do a lot more things which we talk about later on, right? Now our actually last step in this series is the code generation. Okay, now when we talk about code generation, we need to keep track of 2 abstractions, at the source and at the destination, because in the source we have variables, we have operands, we have expressions, we have condition operators, we have iterators, we may have the functions. Okay, and in case of destination, we got to talk about the memory locations. You may have variables, but here we have maybe the registers, we may have the stacks, opcodes, addressing modes, and a lot more things. We may have interface calls to the libraries. We have runtime systems, operating system calls. There are a lot of things we have to deal with when we actually convert our intermediate code, optimize intermediate code, I must say, to the code, actual code. Now this code may be the assembly language, which is actually which targets which is machine dependent code. Okay, because this has to take the intermediate representation of the source program and map into the target language. You have to now this here we have to talk about the target machine. Okay, now we may have the variable accesses. Okay, like we have now we have to do the relocatable absolute addresses. We will be talking about in the source some variables. Now we have to relocate them to the actual locations. And there are a lot more things we will be dealing with. We have to do a lot of mappings, okay? Like these identifiers to locations in the memory or in registers we have when we do operations of these, okay? We may have stack, which will talk about functions, and we may talk about addressing modes, how we are accessing these um, addresses and all those things. If we see our diagram here, now the code optimization after done with the code, so we have a code generation where we are using the assembly code, okay? We are saying LDF, that's because of floating point, so that's why it's in F. So we are loading into the register R2 the identifier ID3, okay? That is actually our C, because we had let me write it again, we had A equals to B plus C times 20 times 60 this time. Okay, this is the identifier third. We are loading this into the register second. Then we are multiplying again the floating point multiplication because this C is in the register 2 now. Okay, so we have to multiply it with the 60.0, right? So we, by saying hash, we are saying this is a constant. Okay. Okay, so where is my pen? I'm losing my side of my pen. Anyways, so we have here this is the immediate constant. Then we got whatever multiplication of R2 times 60 into the R2 itself. Okay, so we have to use the minimal registers as well. We don't use we can't use many registers, so we have to be judicious in that. Then we will load whatever is in the ID2 at the address ID2. That's actually the B, okay, because this is ID2. Okay, that will go into the R1 register R1. That's so R1 is holding the B now. Okay, whatever it's the B. Okay, then we got to add the floating point addition of R1 and R2. We add these two guys because this is R1, this is now R2. This is R1 and plus this is whole thing is R2, C times 60. We add them together and that is stored in R1 itself here. Okay, then we store the floating point into the address location of ID1, whatever is in R1, because now R1 holds the A. Okay, and that is the A is actually ID1, so we have to drop into ID1 whatever is R1 holding. Okay, so this way we converted our intermediate code into the assembly code, which may be pertinent to the target machine. Okay, this code is the machine dependent code. Okay, so that's why we call this as a backend. Okay, this is called as a backend because now this is not talking about the program. This is conversion in terms of the machine, and this was on top was the front end or analysis phase. Okay, or analysis phase, and this is the synthesis phase. It synthesizes the code according to the machine. Getting me? Okay. So with this we end the introductory chapter, and we may add a few more things to it. So until next time, Masalam.